Geico makes it easy to get affordable renter's insurance in as little as 90 seconds. And then you'll start to wonder why everything else isn't so fast. Like, why does it take so long to do the dishes? A meal that's gone in 3 requires 45 minutes worth of dishes. Doesn't make sense. But it does make sense to get renter's insurance through Geico. That way, that pile of dirty dishes and the other things you love are covered. Get more with Geico.
Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. The Venus Life Equation, a new framework for the search for life beyond Earth. The exploration of space is driven by a fundamental curiosity about our place in the universe and a deep-seated desire to understand the natural puzzles that surround us. While this pursuit is neither cheap nor easy, it is propelled by a profound motivation: the search for life beyond Earth. The idea that our planet might be the only place where life exists is unsettling, and so we push outward, sending probes across the solar system and deploying landers and rovers to Mars in hopes of finding evidence of extraterrestrial life. Our search is primarily focused on Mars and the icy ocean moons of the solar system. Venus, despite being a hostile environment, also attracts attention due to its similarities to Earth in size, mass, and bulk composition. Both planets exist within what is technically considered the habitable zone, yet their climates have diverged dramatically. While Earth remains hospitable to life, Venus has undergone an extreme greenhouse effect, rendering its surface an inferno. Understanding how two rocky planets, similar in so many ways, could end up so vastly different offers critical insight into planetary evolution and habitability. This knowledge is increasingly relevant as we study exoplanets orbiting distant stars, seeking to determine which might harbor life. In this regard, Venus provides an essential case study for understanding the conditions that could support or extinguish life on other worlds. One intriguing approach to this question was presented at the 2025 Lunar and Planetary Science Conference, where researchers introduced an equation reminiscent of the famous Drake equation, designed to estimate the probability of life existing on Venus and what implications this might have for other planets. The equation, known as the Venus Life Equation, VLE, serves as a framework for assessing the likelihood of life on Venus at different points in time and, by extension, provides a model for evaluating habitability elsewhere in the universe. The Venus Life Equation is structured similarly to the Drake equation but tailored specifically to Venusian conditions. While the values within it are not yet fully quantifiable, the equation provides a structured way to think about the factors that influence the presence of life. Over time, as observations, experiments, and modeling improve, the values within the equation may become more precise. The fundamental purpose of the equation is to create a scaffold for estimating the chances of life on Venus based on observable and testable factors. Venus's history remains shrouded in mystery, yet scientists have gathered significant clues suggesting that the planet may have once hosted conditions suitable for life. Some models propose that Venus might have had a temperate period with liquid water on its surface, possibly for hundreds of millions of years. If this was the case, then land-water interfaces, critical for the origin and sustainability of life, would have been present. This period aligns with Earth's late Hadean and early Archean eons, during which life first emerged on our planet. If life was able to arise on Earth under these conditions, then the possibility that it also developed on Venus cannot be ruled out. This leads to a more controversial idea. If life once existed on Venus, could it have survived to the present day? While the planet's surface is now inhospitable, its upper cloud layers, around 50 kilometers above the surface, possess temperatures and pressures comparable to those found on Earth. Some scientists propose that microbial life might still exist in this relatively temperate region, suspended in Venus's thick, sulfuric acid-laden clouds. The Venus life equation is built upon three primary parameters: origination, robustness, and continuity. These parameters work together in the equation L equals O times R times C, where L represents the likelihood of life existing at a given time. Origination refers to the probability that life arose and established itself on Venus before the time in question. Robustness measures the potential size and diversity of the biosphere over time, and continuity assesses whether conditions favorable for life have persisted without interruption. Each of these factors is influenced by multiple considerations. Origination depends on the probability of life emerging through abiogenesis, the possibility of life arriving via panspermia, and the extent to which life might have spread across the planet. Robustness is shaped by the availability of essential nutrients, such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, CHNOPS, as well as by the presence of energy sources necessary to sustain life. Venus's potential period of plate tectonics could have influenced nutrient distribution, but once it ceased, the availability of these crucial elements would have declined. The diversity of life also plays a role. A more varied biosphere would have had a better chance of surviving planetary upheavals. Continuity, the third factor, depends on the stability of Venus's environment over time, including stellar influences, geological processes, and catastrophic events such as massive volcanic eruptions or asteroid impacts. One of the most significant unknowns in planetary science is whether life on Earth has been continuous since its origin or if it experienced one or more total extinction events before re-emerging. This uncertainty also applies to Venus. If life did originate there, did it persist uninterrupted, or was it entirely wiped out at some point? The value of continuity in the Venus life equation would be 0 if life had gone completely extinct, and 1 if it had endured without interruption. The Venus life equation, like the Drake equation, faces the challenge of working with limited data. Earth remains the only known example of a planet where life has arisen, creating the so-called n=1 problem. Despite this limitation, the framework offers a valuable means of systematically analyzing the factors that influence planetary habitability. By applying insights from Earth's history, we can identify critical uncertainties and direct future exploration efforts more effectively. Ultimately, the search for life beyond Earth remains one of the most compelling scientific endeavors of our time. Venus, once considered a cautionary tale of runaway climate change, is increasingly viewed as a potential key to understanding the conditions that foster life. Whether or not life ever existed in the planet's ancient oceans or still lingers in its clouds remains an open question, but the pursuit of an answer continues to drive scientific exploration. As research progresses, the Venus life equation will serve as an essential tool for refining our understanding of habitability, not just on Venus, but throughout the cosmos.